Hi everyone, let's do lesson 6 on symmetry, skewness, and modality. What is the shape of a distribution? When we talk about the shape of a distribution for quantitative data, we're basically talking about the shape of a good histogram for that quantitative variable. All right, so part A, the shape of a distribution. The distribution of a variable in general consists of its possible values, together with their frequencies or relative frequencies. Later on, we'll talk about probabilities. So here, for example, we're talking about the various ages of the US presidents when they became president, and their corresponding frequencies for these age classes. So for example, we had 13 presidents in their early 50s, 12 presidents in their late 50s, and so forth. The shape of a distribution refers to the shape of a frequency or relative frequency histogram for quantitative data. All right, so we're focusing on histograms for quantitative data. And again, the shape for a histogram or distribution may be described by its symmetry, skewness, and/or modality. We'll talk about these issues. All right, what do we mean by symmetry? What do we mean by a symmetric distribution? Well, here's an ideal picture here. Take a look at this nice curve here. What do we often call this kind of curve? We often call it a bell curve, which we see of a lot of in statistics. So think of this as a really smoothed out histogram. Later on, when we talk about continuous distributions, we'll talk about these kinds of smooth curves here. Now, this distribution, again, think of this as a smoothed out histogram here, right, is bell-shaped, and a perfect bell-shaped distribution is perfectly symmetric. So what do we mean by symmetric? We can imagine a vertical line called an axis, and if you have perfect symmetry, the left half and the right half of the curve are perfect mirror images of each other about this vertical axis. So again, the bell curve below is perfectly symmetric because it can be divided into two halves about this vertical axis. The two halves, the left half and the right half, are mirror images of each other, and we have perfect symmetry. Now, we rarely see perfect symmetry. For example, if you look at this frequency histogram for presidents' ages, well, some people might call this approximately symmetric. You rarely get perfect symmetry from real-life data, but some people might call this histogram approximately symmetric. Some people might say not so much. It can be a subjective judgment, which is one reason why some pure mathematicians are annoyed with statistics, because you sometimes have these subjective judgments. Is this about symmetric? Many people would say yes, but some people would say no. Now, this distribution is certainly symmetric. This is a perfectly flat or uniform distribution. So this is a situation where exactly 10% of students in the class scored between 0 points and 9 points. Exactly 10% scored between 10 points and 19 points out of 99 or 100 points. So these students down here did very poorly. So here you had exactly 10% of students in each of 10 classes. Now, this rarely happens in practice, but let's say hypothetically, this is what we see. Then we have a perfectly uniform or flat distribution. And a perfectly uniform distribution is perfectly symmetric. Now, a question for you. Where else might you see a uniform distribution? Let's say you're playing a game of chance. Where else might you see a uniform distribution? If you do what a whole bunch of times? How about if we roll a die 100 times? Roll a standard 6-sided die 100 times. All right. So on the horizontal axis, you would have 1, 2, 3, 4, 5, and 6, the possible values of the die face that shows up. And if you were to actually roll a die 100 times, and do a frequency histogram, or perhaps a relative frequency histogram, let's say a relative frequency histogram, then for a standard six-sided die, you should get about 1/6 ones, about 1/6 twos. It won't be perfect. 100 is not divisible by 6. It won't be perfect, but it should basically be flat. You have no reason to think like over here. You have no reason to think that you'd have a whole bunch of 3s and 4s compared to the others. Okay. So it should be a roughly uniform distribution. Not perfect, but a roughly uniform distribution. And in fact, the theoretical distribution for die faces would be perfectly uniform. 1/6 proportion for each face. 1/6 probability for each face. So we do see roughly uniform distributions in practice, and sometimes we see perfectly uniform distributions in theory, like the probability theory for rolling dice. Now, what if we don't have a symmetric or an approximately symmetric distribution? We might have a skewed distribution. A skewed distribution is a type of asymmetric, that is a non-symmetric distribution that has a long tail. So all skewed distributions are asymmetric, but not all asymmetric distributions are skewed. For example, this here would be an asymmetric distribution, but it's not skewed in any way. This here is an example of a left skewed distribution, or a distribution that's skewed to the left. Again, think of this as a smoothed out histogram. It's called a left skewed distribution because it has a long tail extending to the left. Now, this can be confusing to people. Remember that the name of the skewness describes the tail. It refers to the tail, because a lot of students might be thinking, well, wait a minute, I see this big lump on the right side. Yeah, so do I. But still, we say that this distribution is skewed to the left, or it's left skewed. The name of the skewness describes the tail. The tail goes off to the left. Now, where do we see left skewed distributions? I can tell you as a teacher, we often see them on the first exam for a class. So for example, this would be a very reasonable example for a relative frequency histogram for test scores for a class, where most of the students get A's, B's, C's, or D's, but then you have a long tail of students who don't do so hot. Maybe students who weren't prepared at all for the class. They did not have the appropriate prerequisites, perhaps. So this often happens on the first exam of a class. But I have a question for you. Think about this. If students are allowed to drop out of the class, the course, what is likely to happen to this shape, this distribution of scores on future tests? So if this is the shape of the histogram or distribution for quiz number 1, and if students are allowed to drop the class, how do you think the shapes will differ for quiz number 2, quiz number 3, quiz number 4, and so forth? How do you think the shapes would differ? How do you think these shapes will change as students drop the class? Well, what's likely to happen is that, the students who are likely to drop the class are the ones who are doing relatively poorly. So the students who are more likely to drop are more likely to be in the long tail here. So the students in the long tail, I feel like it's rather dark humor to put a big cross or X here, but the idea is that many of the students here in this left tail may well drop the class. And perhaps if some students are caught cheating up here, but then they'd be down here, right? I'd knock them down, probably get zeros. So let's say that no one's cheating, all right? Let's say no one's cheating. Well, what's probably going to happen is that you're going to have drops in the long left tail of the class. And then when you look at the remainder of the class, for the later quizzes in the course, it's more likely that the shapes in the later histograms are more likely to be symmetric. They're more likely to be more symmetric. Well, these are examples of left skewed distributions. Well, here's some right skewed distributions. The distribution here is skewed to the right, or it's right skewed. Again, because the long tail extends to the right. We call it right skewed because we have a tail extending to the right. So here's an example of a histogram that exhibits right skewness. And there is one subject I can think of where if you have a test out of, say, 100 points, you may well get a relative frequency histogram that looks like this. There's one subject in mind in particular that's notorious for reducing this kind of shape. I've heard this happening quite a bit in physics classes. I've heard of physics problems where they would have comic characters jumping onto ropes and you have all these different forces and issues at play. I would fail those tests, by the way. But I've often heard of physics exams where a lot of students will be scoring 20%, 30%. And these are students who might be pretty good at physics, actually. So then these are classes where you really hope that the grades will be curved or that something will be done differently with the grades instead of straight scaling. It would be very depressing if these were the only students getting the A's. Okay, so we've talked about issues of symmetry and skewness. Next, we're going to talk about issues of modality, and we'll describe various shapes of distributions. Next time.